Before I forget, let me start recording. So I've just started the recording. So just for the recording purpose, I'm going to split this class into two. The first one is, we go back one slide. It's just the use of some useful tools for astronomy and sciences. And then the second part of the lecture, we're going to continue on with our normal lecture slides. With Lea Labs. What else do you guys use? Kerbal Space Program. That's cool. MATLAB is awesome. I use MATLAB every single day. So, but one of the free and open source software you can use is Stellarium. Stellarium is a sky viewing software, and you can even use it for controlling your telescope. So if you have a telescope that is motorized, you can use Stellarium to check out where certain stars is and point your telescope via Stellarium. You can even use Stellarium to look at star locations of thousands of years ago, and you can even use Stellarium to look where stars and planets will be in thousands of years from now. So let me show you guys a quick demo of Stellarium. I'm just opening it up on my side. So let me see if I can share the screen. Okay, can everyone see the screen? Okay, cool. So this is Stellarium. So it is currently, so this is just a random generated image that I use, but it is where my location is in Johannesburg. So here we can see the sun is setting. Here we can see the moon. So if we can't see any stars out on this simulation, but if we go here, you can see your astronomical calculation window. So here you can see when is the rise time of Ganymede, Jupiter, the moon, the sun. We can look at transits, different phenomena, graphs of whatever you want to do. Let's see, what can we view? So date and time window, here you can set the date, you can set a time. So let's change it to 8 o'clock this evening. So now at 8 o'clock this evening, we can see where everything in the night sky is. So here we can see is Rigel. So let's go a little bit up. There's Canopus, the brightest star in the southern hemisphere. There's Sirius, the second brightest star. Here is Orion, so here we can see the belt of Orion. Here we can see these nebula, and if we click on it, it gives us more information on it. So we can even zoom in on it, and that will give us more information. So this is some really cool software we can use. So yes, we can see Venus. So you can see this is now down on the horizon. So if we go downwards, that's just the ground. So this is some really, really cool software that you guys can use. And it is, so here, for example, is Pleiades. Example, here we can click on Betelgeuse. It will give us more information on Betelgeuse. So this is a really, really cool software that you guys can use every day. So let me open up my slides again. Yes, For's helmet is also a very nice object to observe. And I'm sure you guys all recognize this little mascot. Yes, the Linux mascot's a little tux. So as I discussed last night, I see there's quite a lot of you, especially if you're studying computer science, that makes use of Linux. So for your scientific careers, if you're going to be in a scientific career or in a research career, then Linux will be the way forward. If you're going to end up in a normal corporate job, then it doesn't matter which operating system you use, as long as they use Microsoft Office, then they're happy. But for the scientific community, we use Linux. So the three major operating systems is Windows, Linux, Apple, or Mac. So you can, using each different operating system has its own different merits. So if you're in a corporate world and like gaming, then Windows is the option. But if you are a bit more in the scientific world, then it's going to be Linux and Apple. Linux and Apple is basically the same thing. They both are built on Unix, but the only difference is Linux is open source and Mac is not open source. And then for Linux, there's a lot of different distros you can use. So the distro that I make use of is Ubuntu. And I want to show them, see if I can get this up and running. Come on, let's get this up and running. So are you guys familiar with the terminal on Linux or even Mac? So from a scientific point of view, if you start using Linux, the terminal is your best friend. So that is basically you can control everything on your computer by going without using any graphics. So I'm going to show you, this is a connection to one of my servers going over SSH that's currently at the observatory. So let me rather do this. So let me log into my own profile. Here we can see we are logged into the system. It gives us a brief overview of the system load, memory usage, temperature, how many processes are running, how many users are logged in. So just to give you an idea what machine we are using, this is a 70-core, 72-thread machine. So it is Intel Xeon Gold dual CPU. So it has 18 cores per CPU, 72 threads in total. And we have 756 gigs of RAM available on this machine. So this is a very beefy machine we use for data processing and science. So for example, if we use a overview of what's going on in the system, here we can get a little more information. So here we can see the CPU's currently idle, so it means no one is actually running anything on the server currently. We can see the memory usage, we can see the swap usage. So this is a nice overview of the server. So we can also look at what the different CPU cores are up to. So here we can see, because it's in a server room that's has airflow and kept at 18 degrees Celsius constantly, we can see it sitting at roughly 30 degrees. The highest between 92 and height is 92 degrees, but it's sitting at 30 degrees currently. And then we can also, for example, do a speed test on the machine. So that is currently the download and upload speed on the machine. So this is, so the command so terminal is a very, very nice way of working with this machine. So for example, if you say ls, it lists everything in the directory where we are now. So say for example, we want to look at the installed software. We go to CD, change directory, go to installs, and if we list everything in here, we can see what is installed. So if we go CD and ... we go up one directory. So yes, on Windows it is called command prompt. On Linux and Mac OS, it's called terminal. Yes, so we use Linux. So we have, so all our machines at the observatory runs Linux, and the software we've written to control the telescope also runs on Linux. So for example, we can go up another directory. So here is a bit more users. We can go up another directory. So here we can see where the different installs are and operating system files are. So if we go for an OPT, that is usually where we install software. Here we can see our installed software. Let's go back up in directory. So let's go, for example, the data directory is where we have data. So here we have our data. So from here on, if we say ls-la, you can actually see who owns the file and what is the read-write permissions of each user. But this is a little bit something you don't gonna use right now, but if it helps getting familiar with Linux. So I would recommend install a virtual machine and play around with Linux. The other thing I want to show you guys with Linux is, let's see if I can share the screen. So if you prefer working with a GUI and graphics, then you will see something like this. So for some reason, it looks like the colors is a bit wonky when I'm sharing it, but that's not a problem. So for example, let me show you guys this. So by running this command, I can fire up a graphical instance of MATLAB. And MATLAB is something I use every day for my work. And the other software I'm using is Python in a Jupyter notebook that I also run off the server. So this is just something interesting I thought that I could show you guys. Oh, thank you very much. I didn't see my mic is muted. Can you guys hear me now? Okay, cool. So MATLAB is a software package you can use for simulations. You can use it to do calculations. You can use it to program a few stuff. You can use it for machine learning. You can use it for artificial intelligence. You can use it for data reduction, data processing, signal processing. So it is, for example, very, very powerful. So let's run this script. So the script will just create basically create sine and cosine waves that I program to an FPGA. So you can see our sine, cosine waves. Here we can see our sine waves. Let's see if I can show you. So do this. I can do this. Let's go over here. So another part of, no, you're not going to be giving problems on MATLAB. So this is just something interesting to show you what we use in the scientific community. So another part of MATLAB is called Simulink, and Simulink you can use a graphical interface to do simulations on and to program a few things. So this is currently a simulation I'm working on for a spectrometer I'm developing for the use at Aardbeeshoek. So right now it's opening up everything. So right now here we can see the entire simulation of the spectrometer and each part of the spectrometer that you can simulate. So for example, here is the analog digital converter, and we can go into different subsystems and different subsystems as well for the simulation. But this is just something to show you what you can use in the scientific community. So the name of the program is MATLAB. So unfortunately, it's a paid program, but you guys are lucky because if you use your student number of a deal that university have, you get a big discount. So you can get MATLAB for about between 900 and 1,200 Rand. But a normal license with the appropriate toolboxes you select costs around about 1.2 to 1.5 million Rand for a license. So the scopes out are for monitoring. Yes, you can import MATLAB on Jupyter Notebook and Jupyter Notebook into MATLAB. So open source version of MATLAB is called Octave that you can also use. And did you guys know that CERN, the Large Hadron Collider, they developed their own Linux distro called Scientific Linux? So that is also something you guys can play around with. And I'm sure a few of you are familiar with virtualization. What do you guys use for virtualization software? VirtualBox, Hyper-V, okay, those are good options. Parallels is very good. I personally use VMware, but it gives you a nice idea of how you can get exposed to different operating systems. And one other nice thing is that we are also doing at the observatory for our servers. We have a base server with a base Linux operating system. And then we have different virtual machines running on top of that server. If you need specific tools that needs a specific Linux distro to run, you just fire up that VM and you continue on that way. So that show you into demonstration. So just something to keep in mind. If every tool has a specific purpose, so if you like playing games or ends up in a corporate world, then Windows will be your forte. But otherwise, I'm going to do a lot of Windows bashing in my classes. So you're all probably familiar with Linus Torvalds, the creator of Linux. So computers like air conditioning, it becomes useless when you open Windows. So to recap, recapping what we did last night. So in last night's lecture, we did chapter 2 and sharing the wrong lecture slides. We did chapter 2 and chapter 3. So tonight we are going to look at chapter 4 and chapter 5 of the textbook. But for us to understand what we did last night and what are we going to do, there I'm going to show you 2 videos before we start the lecture slides. So yes, I'm also going to upload these lecture slides. So if Mac and Linux build a car, would it have windows? That's a good one. So let me show you the first video I want to show you guys. So we have talked about different distances in the sky. So I want to show you this.
Hi, I'm Jana Levin. I'm an astrophysicist.
So that is pretty cool, right? So remember, in the first lecture, I also showed you from where we are on campus, zooming out and asking where our place in the universe is. And that is just a better way of representing everything. And in last night's lecture, we started discussing different cycles in the sky. So let's watch a video about that.
Under a dark sky, you can see thousands of stars. If you watch for a few hours, you can see them rise and set as the Earth rotates once a day. And if you go outside the next night at the same time, you'll see that things look pretty much the same as they did the night before. The stars rise and set, Polaris hangs to the north, and so on. One day hardly makes any difference to the sky's appearance. But what if you wait for another night or a week? If you're that patient and observant, you can spot subtle changes in the sky. Let's say a couple of weeks have passed. Remember that star that was just over a tree in the east when the sun set? The one that made you first notice the stars are rising and setting? Go look at it again. If you happen to be out at the same time, you'd expect that star to be in the same place. But it's not. It's actually a bit higher above the tree. And if you look west, stars that were well off the horizon just after sunset last week are now lower. If you wait a month, this effect is even more pronounced. All new constellations will be visible in the sky after sunset. This is because the Earth is going around the sun, literally changing our viewpoint on the sky. The Earth takes a year to orbit the sun once. Every day, it moves a little bit along its orbit. And as it does, from Earth's perspective, distant stars appear to move their positions relative to the sun. So one day we might see a star very near the sun, but the next day the angle is a bit bigger. At some point, about 6 months after we first saw it, the star is directly opposite the sun in the sky. Then the angle starts to shrink again as the star approaches the sun from the opposite side until, after a full year, the cycle repeats. What this means to you, the naked eye observer, is that the stars appear to rise and set at different times over the course of the year. Stars in the east rise about 4 minutes earlier every night, and stars in the west set 4 minutes earlier. A constellation that was entirely below the eastern horizon at sunset one month might be completely visible after sunset the next month. Another way to think about it is that the stars appear to be fixed, and as the Earth circles the sun moves through the stars over the course of the year, making a complete circle around the sky once per year. The path it takes is a reflection of the Earth's path around the sun, a line in the sky. We call that line the ecliptic. That means the sun passes through the same constellations in the sky every year. We give those constellations a special name, the zodiac. Every year during a given month, the sun will appear to be in a certain zodiacal constellation, from Sagittarius through Scorpius, Libra, Virgo, Leo, Cancer, and the rest. Eventually, over a year, the sun returns to Sagittarius and the cycle starts again. But even though we talk about this process in terms of the sun's movement, it's really the path traveled by the Earth that creates this effect, as our perspective moves with it. And of course, the planets move in the sky as well. Mercury, Venus, Mars, they orbit the sun too, and they do so in approximately the same plane the Earth does. If you could see the solar system from the side, it would look flat. So to us on Earth, the planets go around the sky over the course of a year, and they also appear to change their positions relative to the sun and the stars. The inner planets, Mercury and Venus, move so rapidly you can see their motion after a single night. The outer planets are more leisurely, but wait long enough and they too will be seen to move, sliding through the constellations. By the way, the word planet is Greek for wanderer. There's another aspect of all this you might notice over time. You've probably seen a globe and noticed that the axis of it is tilted. That is, it's not straight up and down, perpendicular to how it sits. That's because a globe is modeling the Earth, and the Earth is tilted. The Earth spins on its axis once per day and orbits the sun once per year. But the Earth's axis is tilted with respect to its orbital plane by 23.5 degrees. And this has a profound effect on our planet. Imagine for a moment that the Earth's axis were exactly perpendicular to its orbit, straight up and down. If that were the case, every day, the sun would take the same path across the sky. If you were on the equator, the sun would rise, go exactly overhead, and then set. If you're on the pole, the sun would appear to go around the horizon every day, neither rising nor setting. It would always be twilight. But that's not the case. The Earth is tilted. In the months of June and July, the Earth's north pole is tipped toward the sun. 6 months later, it's pointed away. This affects the path the sun takes across the sky. Instead of it taking the same path every day, in the northern summer, when we're tipped toward the sun takes a higher path in the sky. Because that path is longer, the days are longer too. 6 months later, in December and January, the Earth's pole is tipped away. The sun takes a lower path in the sky, and because the path is shorter, days are shorter too. That's why we have seasons. When the sun is up high in the sky, it shines straight down on the ground, heating it better. And days are longer, so it has more time to heat us up. It gets hot. In the winter, it's the reverse. The sun is lower, so it can't warm us up as efficiently, and it has less time to do so. It gets cold. There you go. Seasons. The Earth's axis is tipped. If it weren't, the seasons wouldn't occur, and the temperature of the Earth wouldn't change month to month. There's a common misconception that the Earth has seasons because it orbits the sun on an ellipse, and so it's closer to the sun in summer and farther in winter. While it's true the orbit is elliptical, Earth is closer to the sun in January, on the order of 5 million kilometers or so, than it is in July. It's the angle of the sun's rays that makes winter cold and summer hot, not our distance from the sun. Also, you may know that when it's summer in the northern hemisphere, it's winter in the southern. When the North Pole is tipped toward the sun, the South Pole is tipped away. So northern and southern hemisphere seasons are opposite each other. But nothing in astronomy is permanent. The North Pole's not always going to point toward the sun in June, and Polaris is not always going to be the North Star. That's because our planet's axis is actually moving. Have you ever seen a spinning top start to wobble, its axis moving in a slow circle even as the top itself spins? This is called precession, and the Earth does it too. Our planet spins on its axis once per day, but the axis wobbles, making a very slow circle that takes 26,000 years to complete. This affects a lot of what we see in the sky. For example, Polaris won't always be the pole star. Every year, the pole points a little farther from that star, making a big circle 47 degrees across. For ancient Egyptians, the star Thuban was the pole star, and in about 11,000 years, that position will be held by the bright star Vega. Also, the date the sun is in a particular zodiac constellation changes slowly due to precession as well. When the ancients first thought up this idea, the sun was in Aries on March 22nd. The vernal equinox, what some people call the first day of spring. But due to precession, it's now in Pisces. That's why your astrological sign doesn't match where the sun actually is in the sky. 2,000 years of precession has changed them. One of the many reasons astrology is silly. It's incredible to think about. The Earth, the sun, the stars. They allow us to tell the time and time of year just by looking up and paying attention. This is why the stars were so important to ancient humans. The stars were like a clock and a calendar in the sky, long before we had invented either. We've actually learned a lot about the sky just by looking at it. Of course, some of the stuff I've explained we've learned through other means. The Earth is spinning. Stars have different intrinsic brightnesses, and so on. But all of that knowledge, and far more, got its start by people who went outside and looked up. Later, as we applied math and physics to what we observed, we learned even more, and could then go back and explain what we saw. So don't discount naked eye astronomy. It's all we had for thousands of years. In fact, I think we lost something when we started using clocks and calendars and moving to cities with bright lights that washed away the stars from the sky. Those folks long ago were tied to the sky. They knew it like you know the streets in your neighborhood. They could see the stars rise and set. They knew the glory of the Milky Way sprawled across the heavens, even if they didn't know exactly what it was. We do know now with our knowledge gained over the centuries, but it comes at the cost of losing touch with the sky, not living under it as much as we once did. I've spent thousands of hours over my life at night just simply looking up, watching the stars, appreciating the universe as I can see it. The things I have witnessed have shaped my life and instilled in me a permanent and endless sense of wonder and joy. The universe belongs to everyone. Go outside, and if you can, soak up your share. Today we talked about cycles. As the Earth goes around the sun, we see
So hopefully this explained a few of the concepts that we did last night and in the last week a little bit better. are you guys still following? So yes, I will share the video on Discord. And then there's one final video I also want to show you tonight. But before I do so, do you think our sun moves through our own galaxy? Yes, our sun orbits the center of our galaxy, but how do you say will that look like? So let me show you a quick video of how it looks like when the sun is orbiting the center of our galaxy. So from this video, this is a nice animation of how we are moving. So all the planets is orbiting around the sun, but the sun is orbiting around our own solar system, around our own galaxy, the Milky Way galaxy as well. Yes, so our solar system moves. So our sun is orbiting the center of the galaxy. No, and something interesting is we also don't know where the center of the universe is. Now, come on, so let's see, I'm struggling for this to share. Can everyone see the lecture slides? So everything basically moves in the universe. Question, do I play Kerbal Space Program? I've seen a lot of videos about it. My friends played it, but I haven't played it myself. So for tonight's lecture, we are going to look at chapter 4 and chapter 5. So in chapter 4 and chapter 5, we are going to look at the origin of modern astronomy, classical astronomy, and Newtonian astronomy. So what do you guys think is the difference between these three? Newton is not entirely wrong. Yes, Newtonian would revolve around these laws. The way astronomy was perceived over time, yes. So as I said last night, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are all made of star stuff, and that was said by the legendary Carl Sagan. How did humanity first realize that we live on a planet moving through space? That required a revolutionary overthrow of an ancient and honored idea of Earth's place. By the 16th century, many astronomers were uncomfortable with the theory that Earth sat at the center of a spherical universe. So some of the most important figures with the history of astronomy is Nicholas Copernicus, Galileo Galilei, and Sir Isaac Newton. In this chapter, we are going to investigate 4 questions. How did classical philosophers describe Earth's place in the universe? How did Copernicus revise that ancient concept? Why was Galileo condemned by the Inquisition? How did Isaac Newton change humanity's views of nature? And then a quote from William Whewell. Astronomy is the only progressive science which the ancient world produced. How you would burst out laughing, my dear Kepler, if you would hear what the greatest philosophers of the gymnasium told the Grand Duke about me. So that is a letter by Galileo Galilei that you can go read up in your own time. But as early civilizations developed, great philosophers struggled to understand the movements of the sun, moon, and planets. Later mathematical astronomers made precise measurements and computed detailed models in their attempts to describe celestial motions. It took hard work and years of effort, but a passion of astronomy gripped some of the greatest minds in history and drove them to try to understand the sky. The first theme we will be investigating is the struggle to understand the place of Earth in the universe. It seemed obvious to the ancients that Earth was the center of everything. But today, you know that's not true. The debate over the place of Earth involved deep theological questions and eventually led Galileo before the Inquisition. The second theme we will investigate is the long and difficult quest to understand planetary motion. Astronomers built more and more elaborate mathematical models, but I still could not predict precisely or explain the motion of the visible planets along the ecliptic. That mystery was finally solved when Isaac Newton described gravity and orbital motion in the late 1600s. So the great philosophers of ancient Greece wrote about many different subjects, including what I saw in the sky. Those writings became the foundation on which later astronomers built modern astronomy. So, Aristotelian universe is the first concept we look at. Do you know who these 2 figures is? No. Any volunteers? Yes, Aristotle and Plato. So the Aristotelian universe, the first principle. The first principle is something that is held to be obviously true. Once a principle is recognized as true, whatever can be Logical derived from it must also be true. Can you guys think of any first principles? So a good idea is Newton's laws of first principles, yes, but let's go back to mathematics. If you derive something, so take the first derivative, you guys remember doing it from first principles? And that is the exact same thing. So whatever is derived from there is also true. So that is what a first principle is. For 2,000 years, the minds of astronomers were shackled by a pair of ideas. The Greek philosopher Plato argued that the heavens were perfect because he considered the only perfect geometrical shape to be a sphere. And the turning sphere carries a point on its surface around in a circle. And because the only perfect motion is uniform motion, Plato concluded that all motion in the heavens must be made up of combinations of circles turning at uniform rates. This idea was called uniform circular motion. Plato's student Aristotle argued that Earth was imperfect and lay at the center of the universe. Such a model is known as a geocentric universe. His model contained 55 spheres turning at different rates and at different angles to carry across the sky at 7 celestial objects called planets at a time, so the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn. Aristotle was known as the greatest philosopher in the ancient world, and for 2,000 years his authority limited the imaginations of astronomers to uniform and circular motion and geocentrism. So, a hint for the test and the exam, I might ask you, what is uniform circular motion, or what is the geocentric universe? So this is the model of the Aristotelian universe that he came up with. So now we are going to back to first principles and the Aristotelian universe. So how do you determine the distance of an object in space? So in one of our first videos and lectures, we looked, if you take your left hand and you stretch it out in front of your face and you close your right eye and you look through the left eye, you block the figure. But if you keep your hand the same place and you close your left eye and lift your right eye, you see the object far away looking at has shifted a little bit. So that means your two eyes are seeing this a little bit differently. And yes, Mr. Melville, you are correct. This principle is called parallax. So early astronomers believed that Earth did not move because they saw no parallax. The apparent motion of an object caused by the motion of the observer. To demonstrate parallax, close one eye and cover a distant object with your thumb, held at arm's length. Switch eyes and your thumb seems to shift position as shown at left. If Earth moves, they reasoned, you should see the sky from different locations at different times of year. And you should see parallax distorting the shapes of the constellations. They saw no parallax, so they concluded Earth does not move. Actually, the parallax of the stars is too small to see with the unaided eye. So uniform circular motion has to do with the centripetal acceleration of the Earth? No, not really, but we will discuss that later on in this chapter. So every 2.14 years, Mars passes through a retrograde loop. Two successive loops are shown in a figure we're going to look at now. Each loop occurs further east along the ecliptic and has its own shape. Simple uniform circular motion centered on Earth could not explain retrograde motion. So ancient astronomers combined uniformly rotating circles, much like gears in a machine, to try to reproduce the motion of the planets. So what is meant with retrograde? So because Mars orbits faster than Earth around the Sun, so when Mars is approaching towards Earth, it will look like, because it's orbiting faster, it looks like it's approaching Earth, approaching Earth, approaching Earth, and then Earth will overtake it again. Then it looks like it's going back, and it will overtake again. And that is called retrograde motion, and that happens twice. So planetary motion was a big problem for ancient astronomers. In fact, the word planet comes from the Greek word for wanderer, referring to the eastward motion of the planets, including the moon and the sun, against the background of the fixed stars and constellations. The planets do not, however, move in a constant rate, and they could occasionally stop and move westward for a few months before resuming their eastward motion. This backward motion is called retrograde motion. Simple uniform circle motion was centered on Earth, could not explain retrograde motion. So ancient astronomers combined uniformly rotating circles, much like gears in a machine, to try to reproduce the motions of the planets. So are you guys happy with the explanation of retrograde? Okay, so for those that says no, so basically what happens is, remember, our orbits around the sun are in an ellipse. So meaning some parts of the ellipse move, the planet moves faster than others. So for example, in this point here, so let's, for example, we are right here in 16th April. So we will see, for example, Mars approaching Earth. Depending where it is in its orbit on the ellipse, then Earth will overtake Mars again. So that will seems like Mars is moving in the opposite direction. And then depending where Mars is in the orbit, it might speed up again and then will overtake Earth again. So it looks like it's going past us, then going back and going past us again. And that happens 2 times during the orbit, and that will happen with all planets in orbits closer to the sun. So we won't see any retrograde motion, for example, planets further away from us, but we'll usually see retrograde motions of planets close to Earth, for example, Venus and Mars, and definitely planets closer to the sun. So what causes retrograde motion? It's basically just the orbit around the own sun, because we are orbiting not in a perfect circle, but in an ellipse. And later on, we will quickly go over Kepler's laws, and from Kepler's laws, it will be apparent why that is happening. So uniformly rotating circles were key elements of ancient astronomy. Ptolemy created a mathematical model of the Aristotelian universe, in which the planet followed a small circle called an epicycle that slid around a larger circle called a different. By adjusting the size and rate of the rotation of the circles, he could approximate the retrograde motions of a planet. So you can see it in the illustration on the right. To adjust the speed of the planet, Ptolemy supposed that Earth was slightly off-center, and that the center of the epicycle moved such that it appeared to move at a constant rate, as seen from a point called the equant. To further adjust this model, Ptolemy added small epicycles, not shown here, riding on top of large epicycles, producing a highly complex model. So Ptolemy's great book, Mathematica Syntax, published around the year 140, contained the details of his model. Islamic astronomers preserved and studied the book through the Middle Ages. They call it Al-Majestis, so the greatest. When a book was translated from Arabic to Latin in the 12th century, it became known as the Almagest. The Ptolemaic model of the universe, shown below, was geocentric and based on uniform circular motion. Note that Mercury and Venus were treated differently from the rest of the planets. The centers of the epicycles of Mercury and Venus had to remain on the Earth's sun line as the sun circled Earth through the year. Equants and smaller epicycles are not shown here. Some versions of the model contained nearly 100 epicycles, added by generations of astronomers, trying to fine-tune the model to better reproduce the observed motion of the planets. Notice that this modern illustration shows rings around Saturn and sunlight illuminating the globes of the planets, features that would not have been known before the invention of the telescope. So from the Aristotelian universe, this is the model they came up with. So then the Copernican revolution happened. So you would not have expected Nicolaus Copernicus to trigger a revolution in astronomy and science. He was born in 1473 to a merchant family in Poland. Orphaned at the age of 10, he was raised by his uncle as an important bishop, who sent him to the University of Krakow, and then to the best universities in Italy, where he studied law and medicine. Nevertheless, he had a passion for astronomy even as a student. Sometime before 1514, he wrote an essay proposing a model of the heliocentric universe, in which the sun, not the earth, was the center. And can you guys what this caused? And what other revolution this caused? So yes, Mr. Melville, you are correct, and the others as well. So you are correct. So this caused backlash from the church, specifically the Roman Catholic Church of the day, because they believed that we are the center of everything, and not the other way around. So many people were scared to accept this heliocentric universe, or to say it is correct, because they would be executed by the state or executed by the church for saying that the earth and we are not the center of everything. So this was a major, major revolution. So in the Copernican system, Earth moves faster along its orbit than the planets that lie further from the sun. Consequently, Earth periodically overtakes and passes these planets. To visualize this, imagine that you are in a race car, driving rapidly along the inside lane of a circular racetrack. As you pass slower cars driving in the outer lanes, they fall behind. And if you did not realize you were moving, it would look as if the cars in the outer lanes occasionally slowed to a stop, then backed up for a short interval. So this explains retrograde with the Copernican model. So right now, for example, we will see, for example, Mars. We will be approaching Mars, Earth. So that means it will seems like Mars is moving forward, moving closer, then we will overtake Mars, so that we see Mars is moving backwards again. And then it will both see it, we are moving forward and Mars is moving forward. So the Copernican model nicely explains retrograde. So Copernicus could explain retrograde motion without epicycles, and that was impressive. The Copernican system was elegant and simple compared with the whirling epicycles and off-center equants of the Ptolemaic system. However, their revolution novice failed in one critical way. The Copernican model could not predict the position of the planet significantly more accurately than the Ptolemaic system could. Copernicus proposed a revolutionary idea when he made the planetary system heliocentric, but he was a classical astronomer with tremendous respect for the old concept of uniform circular motion. In fact, Copernicus objected strongly to Ptolemy's use of the equant because it required that a planet move faster in some places and slower in others. It seemed arbitrary to Copernicus, an obvious violation of the uniform circular motion and the elegance of Aristotle's philosophy of the heavens. Copernicus called equants monstrous because they undermined both geocentrism and uniform circular motion. In devising his model, Copernicus demonstrated a strong belief in uniform circular motion. Although he did not need epicycles to explain retrograde motion, Copernicus quickly discovered that the sun, moon, and planets suffered other small variations in the motions that he could not explain using uniform circular motion centered on the sun. Today's astronomers recognize that those variations are the result of planets following slightly non-circular elliptical orbits. But because Copernicus had firmly to uniform circular motion, he had to introduce small epicycles to try to reproduce those minor variations in the motions of the sun, moon, and planets. The Copernican model is inaccurate. It includes uniform circular motion and consequently does not precisely describe the motions of the planets. But the Copernican hypothesis that the universe is heliocentric is correct. Considering how little astronomers of the time knew of other stars and galaxies, the universe that Copernicus knew was heliocentric, in that a planet circled the sun and not Earth. So the Copernican universe was elegant in its arrangement and its motions. Mercury and Venus are treated like all other planets, and orbital velocities, so in the blue arrows, decrease smoothly from that of Mercury to the fastest to that of Saturn, the slowest. Compare the elegance of this model with the complexity of the Ptolemaic model as shown in one of the previous figures. The Copernican hypothesis solved the problem of the place of, but it didn't explain planetary motion. If planets don't move in uniform circular motion, how do they move? The puzzle of planetary motion was solved during the century following the death of Copernicus through the work of two men. One compiled the observations and the other one the analysis. So the first of these two men, first is Tycho Brahe. Although Tycho officially studied law at a university, his real passions were mathematics and astronomy. And early in his university days, he began measuring the positions of the planets in the sky. In 1563, Jupiter and Saturn passed very near each other in the sky, nearly merging into a single point on the night of August 24. Tycho found that the Olfson tables were full month in error, and that the Prutenic tables were in error by number of days. In 1572, a new star, now called Tycho's supernova, appeared in the sky, shining more brightly than Venus, and Tycho carefully measured its position. According to classical astronomy, the new star represented a change in the heavens and therefore had to lie below the sphere of the moon. Tycho even thought he believed in a geocentric universe, understood that. The new star should show parallax, meaning that it would appear slightly too far east as it rose and slightly too far west as it set. But Tycho saw no parallax in the position of the new star. So he concluded that it must lie above the sphere of the moon and was properly on the starry sphere itself. This contradicted Aristotle's conception of the starry sphere as perfect and unchanging. No one before Tycho could have made this discovery because no one had ever measured the positions of celestial objects so accurately. Tycho had great confidence in the precision of his measurements, and he had studied astronomy thoroughly. So when he failed to detect parallax for a new star, he knew it was important evidence against the Ptolemaic theory. He announced the discovery in a small book, De Stella Nova, published in 1573. So, you guys recognize this guy. Yes, that is Johannes Kepler. And I'm sure for you guys that did science in high school that you cover Kepler's three laws. Okay, so I'll give you a brief overview of Kepler's three laws. But in your physics courses now, in the next couple of months, you will do Kepler's laws in great depth. So, such as Newton's laws, Kepler has three laws as well. So the one is, the orbits of the planets are ellipses with the sun at one focus. Number 2, a line from a planet to the sun sweeps over equal areas in equal intervals of time. And then number 3, a planet's orbital period squared is proportional to its average distance from the sun cubed. So let's look a little bit deeper at this. So Kepler's first law, each planet's orbit about the sun is an ellipse. The sun's center is always located at one focus of the orbital ellipse. The sun is at one focus. The planet follows the ellipse in its orbit, meaning that the planet to the sun distance is constantly changing as the planet goes around its orbit. So this is how it will look like. So you can see here, this is an ellipse, and the sun is not in the center of the ellipse, but off to one side called a focus. So all planets move about the sun in elliptical orbits, having the sun as one of the foci. You guys still following? Okay, so Kepler's first law is straightforward. So Kepler's three laws might be a good question for the test and exam. So Kepler's second law, the imaginary line joining a planet and the sun sweeps equal areas of space during equal time intervals as the planet orbits. So basically that planets do not move with a constant speed along their orbits. Rather, their speed varies so that the line joining the centers of the sun and the planets sweeps out equal parts of an area in equal times. The points of nearest approach of the planet to the sun is termed perihelion, and the point of greatest separation is aphelion. Hence, by Kepler's second law, a planet is moving fastest when it is at perihelion and slowest at aphelion. So if we visualize this, what this basically means is, here we have our ellipse, here we have the sun at one foci. So now we can divide this into areas. So here we have one area, here we have another area. So that means at perihelion, closest to the sun, this is perihelion, and this is aphelion. So that means the planet orbiting will orbit slower here, and the planet over here will orbit faster. But these two areas are the exact same size. So in this case, this is 1 month, this is 1 month. And to keep it that way is here the Earth will, whatever planet will orbit faster around the sun, and here it will orbit slower around the sun. And that is Kepler's second law. Everybody following and understanding? Awesome. Then the third and final law. So Kepler's third law, the squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axis of their orbits. So Kepler's third law implies that the period of a planet to orbit the sun increases rapidly with the radius of its orbit. Thus we find that Mercury, the innermost planet, takes only 88 days to orbit the sun. The Earth takes 365 days, while Saturn requires 10,759 days to do the same. Although Kepler hadn't known about gravitation when he came up with these three laws, they were instrumental in Isaac Newton's deriving his theory of universal gravitation, which explains the unknown force behind Kepler's third law. Kepler and his theories were crucial in a better understanding of our solar system dynamics and as a springboard to newer theories that more accurately approximate our planetary orbits. So Kepler's third law, the squares of the sidereal periods of the planets are directly proportional to the cubes of the main distances from the sun. So basically what this means is, in sweet and short, the closer the planet is to the sun, the faster its orbit around the sun will be. And the further away a planet is from the sun, the slower their orbit around the sun will be. And the relationship we have, the better formula, is this one. So the planet's orbital period squared, so the orbital period around the sun, is proportional to the average distance to the sun cubed. Now, you don't need to know the formula, just the definition or explanation of the three laws. So from this, we can see the orbital period in years. And here we can see the semi-major axis, so the distance from the sun in AU. So here we can see Mercury, Venus, Mars, Jupiter. So the further the planets are away from the sun, the bigger the distance is and the slower their orbit is. And here we can see the 4 largest moons of Jupiter well orbiting the sun. So planetary motion, so the Rudolphine tables. So the Rudolphine tables was Kepler's masterpiece. It could predict the positions of the planets 10 to 100 times more accurately than the previous tables. Kepler's tables were a precise model of planetary motion that Copernicus had sought but failed to find. The accuracy of the Rudolphine tables was strong evidence that both Kepler's laws of planetary motion and the Copernican hypothesis for the place of Earth was correct. And now we are going to discuss a little bit about Galileo Galilei. So most people think they know 2 facts about Galileo, but both facts are wrong. They are common misconceptions. So you have probably heard the term, Galileo did not invent the telescope and he was not condemned by the Inquisition for believing that Earth moved around the sun. Then why is Galileo so famous? Why did the Vatican reopen his case in 1979, almost 400 years after his trial? As you learned about Galileo, you will discover that his trial concerned not just the place of Earth and the motions of the planets, but also a new and powerful method of understanding nature, a method called science. The telescope was apparently invented in 1608 by lensmaker Holland. Galileo, hearing descriptions in the fall of 1609, was able to build telescopes in his workshop. In fact, Galileo was not the first person to look at the sky through a telescope, but he was the first person to apply telescopic observations to the theoretical problem of the day, the place of Earth. So what Galileo saw through his telescope was so amazing that he rushed a small book into print, Sidereus Nuncius. So to translate it means the story messenger. Reported 3 major discoveries. Remember, these 3 major discoveries of Galileo is also something I can ask in a test and exam. So first, he discovered the moon was not perfect. It had mountains and valleys on its surface, and Galileo even used some of the mountain shadows to calculate their height. Aristotle's philosophy held that the moon was perfect, but Galileo showed it was not only imperfect, but was a world with features like Earth's. The second discovery reported in the book was that the Milky Way was made up of myriad stars, too faint to see with the unaided eye. While intriguing, this could not match Galileo's third discovery. Galileo's telescope revealed 4 new planets circling Jupiter, objects known today as the Galilean moons of Jupiter. Just looking somewhere I copied it. So today, Galileo's revealed 4 new planets circling Jupiter. Objects known today as the Galilean moons of Jupiter and keep its moon. Aristotle's philosophy also included that belief that all heavenly motions were centered on Earth. Galileo's observations showed that Jupiter's moons revolve around Jupiter, suggesting that there could be other centers of motion besides Earth. And sometime after Sidereus Minicus was published, Galileo noticed something else that made Jupiter's moons even stronger evidence for the Copernican model. When he measured the orbital periods of the 4 moons, he found that the innermost moon moved fastest and that the moons further from Jupiter moved proportionally slower. Jupiter's moons made up a harmonious system ruled by Jupiter, just as the planets in a Copernican universe were a harmonious system ruled by the Sun. The similarity isn't proof, but Galileo saw it as an argument that a solar system is sun-centered rather than Earth-centered. So was Galileo believed when he published these writings, or was it regarded as witchcraft? So basically during that time, people didn't believe it, especially the Vatican and the Roman Catholic Church. So yes, it was seen as a form of witchcraft. In the years following publications of Sidereus Nuncius, Galileo made 2 additional discoveries. So from this image, can you guess what one of these discoveries are? Yes, sunspots. So through his telescope, he discovered sunspots. And the second discovery is he discovered that Venus had phases that looks like the phases of the moon. So did you guys know Venus had phases? So Venus has phases. So as Venus orbits around the sun, we can see the sun lighting up a certain part of the planet. And where it is in its orbit, depending on how we see the angle we see Venus. So it appears that Venus will have phases. So in figure A, if Venus moved in an epicycle centered on Earth, the sun line, so see the right-hand page of concept art 4A, it would always appear as a crescent. But in image B, Galileo's telescope showed that Venus goes through a full set of phases, proving that it must orbit the sun. So how did he look at the sun? Though the same as we did. So you take the sun, and you hold a piece of paper on the eyepiece, and then you will see the sun on the paper with the sunspots. I will see at some point if I can do the experiment with you guys. So if we can see here in A, if it didn't orbit the sun, we would only see a crescent phase. But as it orbits, we can see the phases of Venus. So Galileo's telescope revealed such things as craters on the moon, phases of Venus, and the existence of 4 moons orbiting Jupiter. He demonstrated his telescope and discussing his observations with powerful people. He explained how observational evidence could be used to test the prevailing Earth-centered model of the universe. Some of the viewers thought the telescope was a work of the devil and would deceive anyone who looked. Galileo's discovery produced intense and in some cases angry debates. He was condemned by the Inquisition in 1633. So these are the 4 moons of Jupiter that he drawn in his notebook that he saw through his telescope. And then we get to Sir Isaac Newton. The problem of the place of the Earth was resolved by the Copernican revolution, but the problem of planetary motion was only partly solved by Kepler's laws. For the last 10 years of his life, Galileo studied the nature of motion, especially the accelerated motion of falling bodies. Although he made some important progress, he was not able to relate his discoveries about motion on Earth to that in the heavens. The final step fell to Isaac Newton. He made most of his discovery in optics, mechanics, and mathematics. Among other things, he studied optics, developed three laws of motion, defined the nature of gravity, and invented calculus. The publication of his work in his book Principia in 1687 placed science on a firm analytical base. So this book, the first edition of this book of him, I think is still at display at Oxford University where Newton was. So the Apple story was lying. The Apple story was actually true, and he talked about it in this book, the Philosophia Naturalis Principia Mathematica. So you can actually download this book as well. So in the pages of this book, you can see he talked about orbital motion. So this book is at display at Oxford University, if I'm not mistaken. But yes, you can get a PDF version for free if you just search for it on the net somewhere. So if we put this together on a time scale from where everything was developed, we can see the 99 years between the death of Copernicus in 1543 and the birth of Newton in 1642 marked the transition from the ancient astronomy of Aristotle and Ptolemy to the revolutionary hypothesis of Copernicus, and simultaneously the invention of science as a way to understand nature. So here we can see the Copernicus. So here we can see Michelangelo lived in the same time, Leonardo da Vinci, Christopher Columbus. If we go to these 100 years where Galileo are, you can see Tycho Brahe, we can see Kepler, Shakespeare, Elizabeth I, Milton, Guy Fawkes, Rembrandt. Then here we can see the Black Plague of London. Here we can see William Penn, Newton. Then in 1750, George Washington, Napoleon, King George III, John Marshall, Benjamin Franklin. So this puts together where everything that's happened in the past. So Isaac Newton and orbital motion. Newton extracted three laws that relate the motion of a body to the forces acting on it. These laws made it possible to predict exactly how a body would move if the forces were known. So you guys are all probably familiar with the three laws of motion of Isaac Newton. So a body continues to rest or in uniform motion in a straight line unless acted upon by some force. The change of motion of a body of mass is proportional to the force acting on it. So F equals ma. Then a third law is when a body exerts a force on a second body, the second body exerts an equal and opposite force back on the first body. So I assume you guys are all familiar, happy with and comfortable with Newton's laws. So just to recap them a little bit, if an object is at rest, it will stay at rest unless a net force acts on it. So if an object is in motion, it will stay in motion unless a net force acts on it. Then second law, the more force, the more acceleration. Then the third law, every action has an equal and opposite reaction. And then it comes to Newton's law of universal gravitation. So the law of universal gravitation states that every point mass attracts every other point mass in the universe by a force pointing in a straight line between the centers of mass of both points. And this force is proportional to the mass of the objects and inversely proportional to their separation. So this means this force equals that force, and that is G, the universal gravitational constant, mass to 1, mass times 1 divided by the distance between them squared. And I remember this joke that my first year physics professor made when I was in first year, that said you can actually use Newton's law of universal gravitation as a pickup line because one body will attract another body. So, orbital motion. Newton's laws of motion and gravitation make it possible to understand why the moon orbits Earth and how the planets move along their orbits around the sun. You can even discover why Kepler's laws work. To understand how an object can orbit another object, it helps to describe orbital motion as Newton did, as a form of falling. As an object orbiting Earth is actually falling, being accelerated towards Earth's center, the object continuously misses Earth because of its orbital velocity. To follow a circular orbit, the object must move with circular velocity. And at the right distance from Earth, it could be a very useful geosynchronous satellite. So, speaking about orbital mechanics. So if you look at a satellite in orbit, what you need to do to go into an higher orbit? Yes, you are correct. So you move faster. So if you're going up and down in an orbit, it has nothing to do with taking your spaceship or your rocket or your satellite and pointing it upwards and pointing it in a certain direction. It all depends on your speed. So if you increase your speed, the higher your orbit will be. If you decrease your speed, the lower your orbit will be. So for example, if you have a cannon, if we shoot it at a slow velocity, it will just fall back in. If we shoot it at a higher, faster velocity, it will continue on until we can reach an orbit around Earth. So that is basically orbital mechanics, and orbital mechanics can become complicated, but that is the sweet and short of it. So for example, if you are in a Crew Dragon of Falcon 9 and you'll want to be in higher orbit, your first thing is you need to increase your speed to go to higher orbit. If you want to go to lower orbit, you need to decrease your speed. And so for example, the International Space Station loses a bit of its orbit every year, so it needs to be pushed into higher orbits to remain in a constant orbit. So what do? They use retro boosters or thrusters to increase the speed of the space station, and that will push it up to a little bit of a higher orbit. So what would happen if you went against the orbit? So it doesn't matter. So if you go in orbit, you can go in any direction you want to. Everything just depends on the speed you are traveling at. So, geostationary orbit. Can you think about a satellite that's in geostationary orbit? Some of the GPS satellites are in geostationary orbit, yes, but some of them are not. Some WeatherSats are, some are not. You are correct. But in South Africa, the DSTV satellite is geostationary because you point your DSTV dish at the exact same spot in the sky and the satellite is always there. So what is meant by geostationary is you are in a very, very high orbit, and that orbit around this Earth is exactly as the same speed Earth rotates around its own axis. So that would make it appear that the satellite are in the exact same spot constantly. And that distance you need to be from Earth to achieve it using this orbit is usually around 36,000 kilometers. So to be accurate, you should not say that an object orbits Earth. Rather, the two objects orbit each other. Gravitation is neutral, and if Earth pulls on the moon pulls on Earth. The two bodies revolve around a common center of mass, the balance point of the system. Two bodies of different mass balances at a center of mass, which is located closer, more massive object. As the two objects orbit each other, they revolve around a common center of mass, as shown in the right. So the centers of mass of the Earth-Moon system lies only 4,670 kilometers from the center of Earth inside Earth. As the Moon orbits the center of mass on one side, Earth swings around the center of mass on the opposite side. So are you happy with that idea of the common point that both objects are orbiting? Okay, cool. So finally, notice the difference between closed orbits and open orbits. If you want to leave Earth, never to return, you must give your spaceship at least escape velocity. So it will follow an open orbit. So closed orbits are repeating cycles. The Moon and artificial satellites orbit Earth in closed orbits. Below, the cannonball could follow an elliptical or a circular closed orbit if the cannonball travels at the velocity needed to leave Earth permanently, called escape velocity. It will enter an open orbit, and open orbit does not return the cannonball to Earth, it will escape. Then, as described by Kepler's second law, an object in elliptical orbit has its lowest velocity when it's furthest from Earth, so apogee, and its highest velocity when it's closest to Earth, in perigee. Perigee must be above Earth's atmosphere, or friction will rob the satellite of energy and will quickly fall back to Earth. So, do you guys recognize this starship? Yes, Star Trek, that is the Enterprise and also my favorite starship. So if we are, for example, currently on the Starship Enterprise and on the bridge of the Enterprise, and I give you the command to leave orbit, what would you do? Yes, you will increase your velocity, that it is faster than the escape velocity of the gravitational system or the gravity of the planet. So we can actually calculate it. So circular velocity is the velocity a satellite must have to remain in circular orbit around the larger body. If the mass of the satellite is small compared with the central body, then the central velocity is given by central velocity equals g, the gravitational constant, m, mass of the system, over r, the distance between the two. So in this formula, m is the mass of the central body in kilograms, r is the radius of the orbit in meters, and g is the gravitational constant. This formula is all you need to calculate how fast an object must travel to stay in circular orbit. For example, how fast does the Moon travel in its orbit? The mass of Earth is 5.97 times 10 to the power 24 kilograms, and the Moon orbits at 0.84 times 10 to the power 8 meters from Earth's center. So you plug that into this equation, and we can see the moon travels at 1,020 meters per second. So this calculation shows that the moon travels at roughly 1.02 kilometers along its orbit each second. So this orbiting around the central point causes tides. So Newton understood that gravity is neutral. Earth attracts the moon and the moon attracts Earth. And that means that moon's gravity can explain the ocean tides. But Newton also realized that gravitation is universal, and that means there is much more to tides than just the Earth's ocean. So before continuing about the tides, have you guys ever heard about Earth tide? So we all know the moon causes tides, so the moon pulls the water towards it. But in the same thing, we have tides on the ground itself. In the sea, it's easy to see, because then you have low tide and high tide. But on literally ground, it's not that easy to see, but we have tides on ground itself. So at Hartebeesthoek, we have done measurements. So at Hartebeesthoek itself, when it is high tide, the Earth literally lifts up between 25 and 35 centimeters. So the average at Hartebeesthoek is about 27 centimeters. And when it's low tide, the ground is literally pushed down by 27 centimeters. If you are in more residential areas, so we did the same experiments in Johannesburg CBD and in Pretoria CBD. And due to the foundations, the ground is more stable. But when it's high tide in residential and urban areas, the ground literally lifts up between 2 and 5 centimeters. And when it's low tide, the ground is literally pushed down by 2 to 5 centimeters. And that happens constantly every day when it's high tide and low tide. So how does tides work? So the moon's gravity pulls more on the near side of Earth than on the other side. So here we can see the moon orbiting Earth. So it pulls more on the one side. So subtracting the force on the Earth reveals the small net outward forces that produces a tidal bulge. So here, because the moon is on that side, we'll have a tidal bulge on that side and a tidal bulge on this side. So friction with ocean beds shows Earth and drags its tidal bulges slightly ahead. So this will shift a little bit due to rotation of Earth. So tides are produced by small differences in the gravitational force exerted on the different parts of the object. So the sides of Earth nearest to the moon feels a larger force than the side furthest away. Relative to Earth's center, small forces are left over and they cause the tides. Both the moon and the sun produce tides on Earth. Sometimes they add together and sometimes they partially cancel. Tides can even alter an object's rotation in orbital motion. The sun is roughly 27 million times more massive than the moon, but it lies almost 400 times further from Earth. Consequently, tides on Earth caused by the sun are less than half as high as those caused by the moon. Twice a month at new moon and at full moon, the moon and sun produce tidal bulges that add together and produce extreme tidal changes. High tide is very high and low tide is very low. Such tides are called spring tides. Here the word spring does not refer to the season of the year, but rather to the rapid welling up of water. At first and third quarter moons, the sun and moon pull at right angles to each other and the sun's tides cancel out some of the moon's tides. These less extreme tides are called neap tides, and they do not rise very high or fall very low. The word neap comes from an obscure Old English word nip that seems to have meant lacking power. So these are also two definitions that you can remember for testing exams. So here we can see the different tidal bulges. So here we can see when the moon and sun is both tugging on the water mass of the oceans, we have spring tide because they are combined. So question, what causes the bulge on the other side of the earth? So that causes is if we pull water or a bit of on this side, due to the rotation around Earth and due to Earth is a bit of a rigid body, so that means if you stretch it on one side, there will be a little bit of stretching on the other side as well. So that's why you will have high tide here, low tide here, low tide here. Until the moon reaches this point, you will have high tide, low tide, low tide. So tides are a bit egg-shaped. So astronomers built on the discoveries of Newton, just as he had built on the discoveries of Copernicus, Tycho, Kepler, and Galileo. It is the nature of science to build on the discoveries of the past. And Newton was thinking of that when he wrote, I have seen further. It is by standing on the shoulders of giants. So, can you guys guess who also said this? Yes, you guys are correct. Albert Einstein said this as well. I have seen anything. It is by standing on the shoulders of giants. But there is one other person that has said this as well. And that is Stephen Hawking, because Stephen Hawking built his work on Einstein and Einstein on Newton and so forth. So Stephen Hawking has said the same thing. And there is another one that said this as well, and that is Robert Oppenheimer, the chemist that was leading the Manhattan Project, so the first nuclear bomb. And after they tested the first nuclear bomb, he said, I have become death, the destroyer of worlds. And that, ladies and gentlemen, is tonight's lecture. I hope that you enjoyed the lecture. I will remain active for another minute or two if you have questions. Otherwise, you're all welcome to log off and have a wonderful evening. Enjoy the rest of your week. Before the end of the week, I will have the assignment, test, and exam dates available in the study guide. I will also upload the assignment, but don't worry much about that. In next week's class, I will discuss the assignment with you. But otherwise, have a great evening, and I will see you all next week.